Hello, and welcome to Microsoft Research Webinar. I am Junwon Park, the PM for Microsoft Vision, and with Zygmunt Lenyk, I'll be sharing with you the state-of-the-art computer vision model that we created here at Microsoft. Together, we will discuss the implications of our large pre-trained vision model, how we achieve the state-of-the-art performance, and how you can benefit from the model that we are making publicly available. Without pre-trained vision models, a team that needs to perform a computer vision task would need to first collect a large sum of labeled data, then spend weeks training either a convolutional neural network or transformer model from ground up. For example, if a team needs to identify what landmark is in the image, the team would collect a set of landmark images, label what landmark is in each image, then wait weeks waiting for a model that is specialized in doing this one task to finish training. Then, if the team needs to perform another computer vision task, take for example, detect where an animal is in the image, then the team would need to collect another set of data, animal images, and then label of where animals are in each image. Then wait weeks again training yet another model that can only perform this one specific task. This means that as the team grows and the number of tasks increase, the total cost multiplies. The cost grows linearly with the number of tasks. This also means that if your team invested into getting training data to teach a model about one aspect of the visual world, for example animals, it is not being used to help any other models that may benefit from understanding about animals. For example, a landmark model that can identify a zoo because there are animals in the image. General pre-trained vision models, on the other hand, seek to build a general understanding of the visual worlds, of how images can be projected into the vector space such that their visual meaning is preserved. Instead of learning from a task-specific dataset, for example, just animal images, a general pre-trained vision model would learn from an unbounded domain, such as animals, products, buildings, chairs, books, hand drawings. The objective of building a general model is not to apply the model for one task, but to build a model that learns anything and everything that can be encoded in images, then apply it to any number of vision tasks. Now, when we say that a general pre-trained vision model learns a general visual representation of images, what we mean is that the model learns how to encode pixels into vectors effectively. As an example, one way to build a general pre-trained vision model would be to train a convolutional neural network that learns to perform the image classification task on ImageNet dataset. Once it is trained to predict a diverse set of classes ranging from chairs to animals in the ImageNet, you could freeze the model, remove the last fully connected layer, which would be predicting the ImageNet specific class scores, then use the resulting network to send in images and get back embedding vectors. An effective image encoder can convert images into embedding vectors such that the distance between the vectors would correspond to the disparity between the underlying images. In the example you see, there are 4 images that are converted to embedding vectors by a hypothetical general vision model. In that vector space, the 2 images you see on the left of the Space Needle in Seattle are geometrically near each other in the vector space because they are similar images. Then these images of Space Needle are closer to a palace in Korea than to a mountain in nature, since the buildings are more similar to each other than to a mountain. Once we have trained a model that has a powerful representational capability, we can take the model's general understanding of the visual worlds and apply it to any computer vision task. If a team has a specific set of classes into which they need to classify images, then they can take the image encoder and build a linear classifier on top of it, and get a model that produces good results without having to collect a large amount of data and without having to wait weeks for a model to be trained. Now, if the team does have a large amount of task-specific data, they can further improve the performance by fine-tuning the model. That is, they would unfreeze the pre-trained model, either entirely or partially, then continue the backpropagation to update the parameters in the network. Using a large pre-trained vision model, then further fine-tuning it, is often key to achieving state-of-the-art performance on vision tasks. Through this transfer learning process, a general pre-trained vision model can benefit any number of tasks, such as the examples you see on the slide, ranging from image classification, object detection, image retrieval, and image generation. Here at the Microsoft Bing Multimedia Group, We have both the need and the ability to build a large pre-trained vision model. In order to provide products such as the text-to-image image search, text-to-video video search, and search by image visual search, Multimedia Group has the need to perform tens of vision tasks. This ranges from detecting where an object is in the image, retrieving similar looking images, scoring how aesthetically pleasing an image is, and finding out what landmark is shown in the image. At the same time, Microsoft is operating one of the world's largest search engines and one of the world's largest cloud services. This means that we have the infrastructure capable of storing and processing web-scale data. This combination of the need to perform tens of vision tasks and the capability to build to leverage web-scale data led us to plan to build a state-of-the-art pre-trained vision model, and we think we achieved it. I'm excited to announce to you, on behalf of my team, that we are making the ResNet-50 version of our model available to the public. You can get your hands on this model by going to aka.ms/Microsoft Vision. And you can use this model to advance your deep learning research or build your own computer vision products. We are incredibly happy that we are able to contribute our work to accelerate deep learning research and to support the teams across the planet. To make sure that teams of any size and with any infrastructure can benefit from our work, we trained a version of our model on the ResNet-50 architecture, which is used widely in the academia and in the industry. Now, it is my pleasure to invite Zygmunt, the engineer who is in charge of the Microsoft Vision Model, to walk you through how you can download the Microsoft Vision Model to build an example image classifier. He will also showcase the state-of-the-art performance that we achieved on 5 popular computer vision benchmarks, then explain the engineering techniques that we used to achieve the results. Zygmunt, off to you.
Hello everyone, my name is Zygmunt Lenyk and I work at Bing Multimedia. My main area of focus is the pre-trained vision model. And today I wanted to walk you through an example how using a Microsoft Vision we can very quickly and in a simple way train a classification model that will achieve state-of-the-art results. And today we're gonna use only one GPU and under 10 minutes we'll be able to build a model that will achieve over 92% accuracy score on Cypher 10. And to do that, we'll freeze the Microsoft Vision model and just train a linear classifier on top of the frozen model, which is following a very popular technique of the papers like recent CLIP or other papers from last year. So let's start by necessary imports. This is quite standard. I think the only thing that is interesting here is that we'll be using PyTorch as our backend, and we'll use logistic regression from scikit-learn. Now is the value, the new element that we're adding is developed by us Microsoft Vision Python package. And this is Python package that simplifies your development because in one line we can download the model, transfer its weight to the ResNet-50 architecture, and its interface is based on Torch Vision interface, so it should be very familiar to everyone. Yeah, so let's define how first we'll preprocess the images. This is pretty standard preprocessing method used by all the popular research papers. The only thing different here is that you might notice that we swapped the image channels, which means that Microsoft Vision was trained on images using BGR format, so we need to transform the images to BGR format. As mentioned, we'll be using Cypher 10 for today's example. I've got it already downloaded. And we're using Cypher 10 that is available at PyTorch, so it's so we can very quickly and in one line use this dataset. But please note that this dataset can be replaced with any dataset of your choice without any changes to the rest of the code. So we can plug in any dataset and achieve very good results using the same code. This is the line that actually takes care of the importing the pre-trained Microsoft Vision model. We can see that it's very simple. We define that we want this model to be pre-trained, and actually the only difference between this package and the Torch Vision package is just swapping name Torch to name Microsoft, and everything should work out of the box. To improve the speed of our computation and to use the fact that the features of the Microsoft Vision model are already high quality, we can just set our model to the evaluation mode and do not fine-tune the whole model. We'll just run the forward propagation through our model. And the only thing trained will be the linear layer, the linear regression on top of that model. So we set it to evaluation mode, and we copy it to a GPU so that to increase the speed of computation. And as mentioned, this example is using only one GPU. So this is a setup that anyone could actually follow because it's not too expensive. This method will take care of extracting the features of the dataset. We can see that it works with any model and any dataset. We're passing the dataset to this method, and by using PyTorch data loader, we can also increase the speed of this computation by increasing batch size and number of parallel workers that are fetching the images. And because we're just using the expensive the expensive computation in a forward propagation, we can actually use quite large batch size per GPU, which in here I set to 128. So we copy the images and the labels to the GPU, we run the feature extraction, and we append all the features and all the labels together. And we catenate the results after copying back to the CPU. Yep, so once we have that, we can extract the train features and the labels from the train set, and the same for the test set. Even using one GPU for Cypher 10, this is taking less than 2 minutes. And now is the actual model that we're training. We're creating a logistic regression that is a classifier from scikit-learn package. And also to follow good research practices, we set the maximum number of iterations to 1000, and we also set a random state to a fixed integer, 0 in this case, for our results to be reproducible so that anyone can also validate our scores. We also increase the number of parallel jobs to run this computation to increase the speed. So we fit this model with our training features and to fit it to the train labels, and we predict what are the test features, and then we just simply measure the accuracy of our predictions against the labels. And the accuracy that you should all get out of this is the 92.64 on Cypher 10, and it took us 8 minutes to run that. So again, this is very quick and can scale also on much larger data sets. So let's talk about the deep learning techniques that we use to build this model. The main idea behind it is to use the multitask learning with hard parameter sharing. Hard parameter sharing means that we will share the backbone and share the embedding of the whole model, but we will use multiple classification layers on top of this model. In this particular case, we assembled 4 datasets for training. 2 of them are publicly available, which is ImageNet 22K, which is a larger version and a bit lesser known version of the popular ImageNet 1K, and a Microsoft COCO. We also scraped search engines and created 2 web-supervised datasets. And by this, we mean that we used search query as label for our images, and the images returned by the engines as the dataset. And This idea is actually quite very practical for everyone to use, and very interesting setup, because this is quite common problem that many researchers face, that we want to develop good robust models, and we have multiple datasets available. There are multiple publicly available datasets. We might have datasets of our own, and we have no good way of combining them and efficiently training on all of them in parallel. So our idea was to use this multitask learning and hard parameter sharing, and we showed that by this rather simple setup, we can achieve state-of-the-art results. And this also allows our model to be robust and to be easily transferable between domains. So because we want this model to be used in multiple scenarios, so that you can plug in any of the classification problem or other problems that you might want to use this model for, and this model should perform very well on that datasets. We evaluated our approach on multiple datasets from different domains, including some popular general-purpose datasets like ImageNet or CIFAR or STL, and some more fine-grained datasets like CUB, which is bird detection, flowers recognition, and SVHN, which is actually house numbers datasets taken from street photos. On each of these datasets, we have competitive results. And what I'm trying to say is that whatever your scenario is, Microsoft Vision Model will be a good starting point for you, which you can use even as is just to extract features from your images, or to further fine-tune for even better results. If we average scores on those datasets, we actually outperform any other publicly available models inside the ResNet-50 architecture. And with that, I wanted to pass it back to Junwon. Thank you.
Thank you, Zygmunt. I hope you enjoyed our presentation and that you can leverage our model to achieve amazing results in computer vision. If you are passionate about creating world-class computer vision models, I invite you to visit our career page at aka.ms/beingmultimediajobs. Join us at our team so that you can leverage our web-scale data and our web-scale infrastructure to fulfill your passion. Once again, you can get your hands on Microsoft Vision Model at aka.ms/Microsoft Vision. Finally, we thank our management and leadership, Mark Bolin, Ravi Yada, Kun Wu, Minaz Merchant, Arun Sachati, and Jordi Ribas for enabling us and this work. Thank you, and now we are open to answer your questions. And we are now live, and we will be answering the questions live. We noticed some great questions that you asked during the event that we believe a lot of people watching would be interested in. So we'll begin with these questions. Please feel free to keep submitting the questions in the meantime. The first question is from Karimullah Shaikh, who asked about what is the objective function that Microsoft Vision Model was learned on. Zygmunt, would you describe the objective function, aka the loss function, the batch size, learning step size, any other hyperparameter that you can share?
Sure, I can share that. I know there are quite a lot of very similar questions about the technical details on our approach, and since we didn't publish a paper, at least yet, I know it may be quite mysterious so far, but so about objective, as I mentioned in the presentation, we used multiple data sets, and all of those data sets were classification data sets. So for all those, so the objective functions were cross entropy for all those data sets, but it was for each data set was optimized separately. As for other technical details, what was important that we used quite large batch size for this, because we wanted to, each batch was consisting of all of examples of images from each data set. So large batch size was ensuring that each data set was sufficiently represented in each batch. And then for the training steps, we used cosine annealing, learning rate decay, and we started with learn rate 0.2. I believe that's it.
Great. Next question is from Rashid Moin from Microsoft. What is the minimum size of the dataset that you may want to further fine-tune?
I'm not sure if I'm reading the question correctly.
Yeah, so I guess in general, let's describe what would be your advice on, given any organization on Earth or any person trying to solve a vision task.
Yes.
How should they determine whether they should fine-tune this model further or just take the pre-trained model?
Yeah, so as Junwon mentioned, there are a couple ways that we can approach this. Depending on the resources that we have, we might want, if we have more resources, we might want to take our model and fine-tune it fully to our new task. Or if we're happy with putting less resources in and just want to use model as is, we can use it as feature extractor or just to learn one linear layer on top of that model. Those are the three most general approaches to this. And per dataset, the target dataset size that we might want to use it, I don't believe there should be any problem with minimal size. Obviously, if that dataset will be very small, then you might have better chance without training any additional layer, because then that additional layer would have very little training data to learn on. But you might want to use the model as a feature extractor only, and then just do zero-shot classification using just the features if your data is sufficiently small. And when I say sufficiently small, some of the tests that we've run, that we also shared, were on the dataset of sizes as small as a couple thousand training examples. So this should be sufficient to learn one linear layer on top. But if we're going much smaller to hundreds or even tens of images, you might want to turn into zero-shot classification.
Next question. Is logistic regression sufficient, or do you need other classifiers for certain tasks?
So logistic regression will work well in our scenario of classification, especially this larger scale classification, that we use, for example, for ImageNet. So this is, we could say, sufficient. And the question is, what is the return that you want to get from this model? So mentioned you can run it in a zero-shot classification that you just use it to extract the features. Then the next kind of cost that you can pay is to train this logistic regression to improve the performance of that a little bit. And then every other layer that you will start adding will have diminishing results, return of your investment. So I would say generally it is sufficient, but especially for very specialized tasks, you might want to add on top more layers to allow them more specialized knowledge.
What is the footprint of this model in terms of memory size?
Oh, this model that we published is the regular ResNet-50. So the model itself, I believe it takes less than 100 megabytes. I mean, I hope that we, if that the question was about storage of the model. Of course, there is some memory limitations when we run the model in production. But ResNet-50 is generally quite compact model, and so you shouldn't have any troubles with running this on reasonably. We run it on the batch sizes like on one GPU. You will be able to squeeze in batch size as large as, I think, 1,000 if you do just forward propagation.
Then the next question is the order of the tasks that you train important in the multitask training setting?
General answer is no. Tasks are optimized at the same time, and so there is no order to the tasks. They are in each batch is having examples from each data set. Yeah, so that's the short question. Short answer. Mm-hmm.
Next question is, how do we know how many layers that we should freeze and how many layers to keep open for further fine-tuning?
That's actually a very good question, because the answer to the question is not simple. So to be able to compare our results with other research, we evaluated it with one linear layer on top of our model, and with no further fine-tuning, right? But depending on your task, you might want to actually freeze some layers, unfreeze others, and fine-tune the others. And there is, like, I would say, the whole separate branch of research that tries to optimize and fine-tune that part. So I'd say the answer for that is not straightforward. We in Bing, we had success with both freezing that model, but also freezing that model fully, but also when we unfroze some of the layers, like when you look at the ResNet-50 architectures, you can unfreeze the whole blocks. So ResNet-50 consists of 4 blocks, and we see the results of model improving if you train, for example, only last block or last 2 blocks of the ResNet-50. So there are absolutely, you have to experiment with this, and there are definitely gains to be gotten this way.
Next question is from Alexander Kuzmenko from Grid Dynamics. It was mentioned that you have datasets of various sizes. How did you weight the multiple loss functions in this case?
Yes, so each dataset, the way I would say the weight it contributes to the final loss is proportional to its size. So at the end of the day, if some data set is 2 times larger than the other, its loss will contribute twice as much as a smaller data set. This is also very interesting because we can see this very clearly in our evaluations and the loss functions that loss functions for each data set, that we can see that it's first easy for the model to start optimizing those large data sets. And then when this flattens, you can see that the loss functions and the model is looking for those optimizations in smaller data sets. So this is kind of how we would expect model to behave here.
Then next question is, how did multiple dataset composition work with small batches?
Yeah, that's exactly. The short answer is it didn't very well. So increasing batch size here was crucial, and using like when we were trying with batch sizes like 128 or 254 and or even 520, 512, we really saw much worse results. And so increasing the batch size to 1,000 and 2,000 was crucial to get good results here.
Then how do you prevent overfitting on small data sets?
So I mentioned that on one side, the model tries to optimize first large data sets, then smaller data sets, and we can see those loss functions going down for all that data set. But at the same time, those data sets for each other, they behave like as regularizers, or to regularize the model for each data set as well. So if you start overfitting on one data set, especially smaller one, it will very soon be visible on larger data set, and the loss on the larger data set will keep from that overfitting.
Next question is from Stanley Moses from Research Studio Austria FG. Based on your experimentation, which of the distance metric has been proven to work well for large-scale image retrieval task?
Short answer is cosine similarity. Yeah, so we've experimented with a few, with some more modern and more classic ones, but cosine similarity works very well for us.
A question from Karimullah Sheikh from Flipkart. What is the metric of evaluation used for embeddings quality?
So for this release, and the result that you can see is we followed the pattern of the CLIP actually paper from OpenAI that was recently released. Sorry, could you actually repeat the question?
Sure thing. It is, what is the metric of evaluation used for the embeddings quality?
Yes, yes. Oh, so yeah. So we train a linear classifier on top of our metric, and then measure the accuracy on the data sets that we listed in the presentation.
And then the next question is, are your labels multi-class or multi-label in the training data?
So the answer is both. Some data sets have single labels, and some have multi-labels. And for multi-labels, we handled it in a way that, let's say that image has 2 labels, then we will assign this one hot vectors to have values of 0.5 to all the labels that are in the label set for each image. So in general case, if the image has n labels, it will have value 1 divided by n for each of that. That will be the target for that model to learn.
Another question is around the architecture. So can this training scheme be used to squeeze more performance by fine-tuning with other commonly established peer architectures of ResNet? Has such attempt been done concurrently to compare how other architectures fare in this regard? I think the general question would be that have you tried other architectures, and what are some general comments that we can make about other architectures than ResNet-50 if they have capability of training a new architecture?
Yes, that's a good question. So as we said, like at the beginning, we mentioned that, okay, we chose ResNet-50 here because we want to showcase that this method works, and this is actually at least as good as other methods out there. But especially when we start to scale to more tasks and larger data sets, your return will be better with larger architectures. So we also experimented with architectures like ResNext 101 or efficient nets, and we see that there is gain on that architectures. So I would say that larger architectures even have a chance to benefit more from that approach than smaller architectures, because there's always the question, okay, how much can we actually squeeze out of ResNet-50? The answer is maybe a lot, but definitely larger architectures are still underfitting to their task, to lots of the vision tasks that they're being given. So they have the capability of very well generalized into multiple tasks within the same architecture.
Next question is, the figure that you had shown for multitask learning has common feature layer for all tasks. How did you handle coarse and fine-grained discrimination variations across the tasks?
Yes, that's a very good question. So naturally, so some of the data sets that we use are more fine-grained and some are more coarse-grained. So I wouldn't say, so normally how you would approach fine-grained recognition is that you would do some metric learning, some contrastive loss. So we didn't do it here. So we kind of treated each task as a classification task, and we saw what kind of can you learn features that will model both fine-grained and coarse-grained those tasks. I wouldn't say any of our methods that we used was specifically designed for fine-grained tasks, but as it turns out, like the architecture that we used, and it allowed us to generalize well into both of those type of tasks.
Next question, how do I interpret the output array of the model? For this one, I guess
of the model, yeah.
I guess you could give a intuitive interpretation of what is being represented in the vectors.
Yes. So I would say it's tough to interpret the output just like by looking at it, and for definitely for humans this will not be possible to say anything about the image. So the output is just a 2048 embedding that was performing well on the classification of one linear layer. So the only thing we as humans can derive from looking at the output is a similarity between two images. We can compare the cosine similarity between two vectors to measure the similarity between images, but I wouldn't go anywhere else with the interpretation of that array.
Next question: Have you attempted to distill the model, or any other compressions?
I'm assuming that what is meant by this question is that we take our model and perform distillation to the other model. So the answer would be no. We didn't do distillation of that model because usually the way you do distillation is that you would take much larger model and then distill into this one. So while this is a valid approach that also could work well in this case, that would definitely put in doubt the kind of integrity of our result. Was that ResNet-50 actually trained on its own, or was it distilled from larger model? So to keep it pure, we didn't do distillation for that experimentation here, but still distillation is definitely is something that we will use internally to obtain as strong models as possible.
Another question from Stanley Moses from Research Studio Austria FG. Stanley has used feature vectors before and had hard time debugging it. Do you have any advice on how Stanley could improve accuracy?
Sure. I mean, I would have to have more details about which results actually didn't perform as expected. We'll definitely publish the notebooks that you will be able to replicate the scores that we published.
Yeah, I think in general, let alone this model, but any vision model that would represent images as embeddings and using that in part of a larger computer vision systems, how would you, imagine somebody runs the system and gets low accuracy, how would you advise them to further debug, find out where it's going wrong, and then improve the system?
Yeah, I think especially in our experimentation, we noticed that really small tweaks can matter a lot in terms of accuracy. So we need to take care of things like proper image normalization. Make sure that the format of the image is the same as expected by the model, because our model expects images in BGR format as opposed to RGB. So I think that first we need to make sure that all those little details are correct. And I hope that the notebooks that we'll publish will help with this.
Yeah, I want to pause for 1 minute and thank everybody for asking great questions. I think we'll be taking about 2 more questions. And then if you have pressing questions, please keep them coming. Unless we see any very important questions, we'll end with the next 2 questions. The next one is from Jezia Zakharoy from Qatar University. You've seen great results by training on many different data sets. What do you expect will happen to accuracy if you train on even more data sets? You already reached 92%. Do you expect it to go even further? Will there be diminishing returns?
Yeah, so I think it's the question of how good our approach will be versus the specialized approach, like the approach that will train on just one data set, right? So if we just train on image set, let's say, then we know that we can get higher results. As you can see, for the PyTorch model trained just on ImageNet has higher ImageNet results than ours. Now the question is how much of this score we can save. We can save by adding more data sets, and so definitely for more general for more general data sets. There will be some loss once we start adding more data sets. So we're looking for this kind of sweet spot of the data sets that we're still generalizing well, but at the same keeping the performance, but at the same time offering us good performance across many tasks. But I would say that for more surprisingly, for more fine-grained and specialized tasks, adding some other tasks might even have positive influence on those tasks, because as I mentioned, those larger tasks often you can treat them as a regularization method to your model, and they are very well preventing overfitting on them. So definitely, while you will be increasing number of data sets, the scores will start to go down, but it has to be considered case by case.
And then the next question is the last question. So Zygmunt, you answered lots of great questions. Hopefully now you can drink water and take a break. Next question is from Faith Wambua, who is a student in Kenya. What approach would you recommend to deblur images before classification by ResNet-50? I think we can take this question a little more general and talk about what are pre-processing techniques that you would use to the image itself before feeding into Microsoft Vision Model.
Yeah, I see your. So we used for training standard image preprocessing, which did not include deblurring images. Images used for our training are usually already quite high quality, so I wouldn't say they needed deblurring. When I say standard preprocessing, I mean like resizing, cropping, and flipping them vertically. But there definitely is value in curating the data set that you use for training, and but I would say it doesn't. You will have much more success by trying to remove the outliers for each class of the for each class of the image. Look for outliers and removing them from the data set, then looking at the images themselves and trying to blur them.
And with that last question, we'll now close the live Q&A. Thanks to all the attendees for coming to our webinar. And once again, as reminders for how you can review and learn more, you can visit aka.ms/Microsoft Vision Model to return to our announcements, aka.ms/Microsoft Vision to return to the model itself, which is a Python package with our example usage code that you saw today. And then aka.ms/Bing Multimedia Jobs if you want to join our team and work on world-leading computer vision models such as this one or fine-grained recognition models that are downstream, object detection, so on. So with that, thanks to everyone for coming and hope to see you in our next announcements.
Thank you very much.